Multicloud is where practically every large enterprise already lives. Most large global organizations today run across some combination of public cloud, private cloud, SaaS platforms, and of course, on-premise data centers. Now, with a global hybrid multi-cloud landscape, life can get a bit complicated. So how do we make sure that all of this runs as one coherent and predictable environment? Today, I'll walk you through 3 architectural principles that I see driving the success of many large global enterprises today. So I have a customer, a manufacturing giant, that recently needed to turn their business around. And by following these principles, they've managed to build a flexible and standardized architecture, helping them, in part, save almost €1 billion in the last years. The reason that this was a major enabler for them is because it helped them make spend decisions that were driven by business needs rather than by infrastructure constraints. But before I go into what works, let's talk about what doesn't work. Now, the first thing we often see is an overly centralized architecture. This can often be because of historical reasons, that there's one hub either globally or regionally, sometimes in a dual site arrangement, but that's doing all the routing for all of the clouds and services that exist in that organization. Now, it's all fine and good if you're a user that works or lives right nearby headquarters, right? But if you happen to be in a different region over here, well, then you're going to have to travel all the way to that hub and then all the way back to access just a local region, right? So that introduces a lot of latency into that user's experience of your environment. It means that they can't do their work necessarily as efficiently as they should be able to. And it also means your network costs are going way up because you're having packets travel back and forth, much longer distances than they otherwise would need to. And of course, this becomes a compliance nightmare if you have data that is sensitive and for whatever reason should have been processed in region and in place. So this architecture is one we see. There is a second one that I like to call primary cloud hairpinning. Now, this is where an organization has a preferred cloud, a favorite cloud that they like to use, and they use this one also for all of their routing. So they're routing all of their services as well through here, even though they have a multi-cloud architecture. Now, this can create a standardized architecture in different regions, so that is an advantage there. But what you do have there is an over-reliance on the public internet and the cloud backbone, right? And what that means is that you're paying a lot of data transit fees interregionally and data egress fees out to wherever you need to bring that data to and from. But you're not necessarily paying for performance. You don't have any control over the network paths that these are traveling. Now, some companies try to solve for this by using cloud-native interconnect technologies, but these don't tend to be globally available. They're often offered only at low bandwidths, and they really depend on bilateral partnerships, which does not put you in control of your network. And in fact, what we start to see with a hybrid multi-cloud environment that's built this way is there have to be a lot of special exceptions made in order to make this work. So you end up with a really inconsistent security profile in a really distributed way that doesn't necessarily work in the long term as you grow and scale. And because all of your network technology choices were informed by that primary cloud and its compatibility there, you end up in a vendor lock-in situation. That means if you decide that's not your primary cloud anymore, you have a huge overhaul that you have to do to make that change happen. So this is not necessarily ideal for enterprise-grade multi-cloud, but if that doesn't scale, then what does? So the first principle that we often see our customers use is that they build a series of vendor-neutral network hubs in densely connected cloud-adjacent metros. And what that gives them is a set of control planes that are abstracted from the clouds and services they're using, but very, very close to them. So that means that they can individually connect these to all of their clouds and services that they're using. And that path will be shorter than if they had everything going to one or the other. Now, in order for this to work, those hubs need to be chosen very carefully. And I mean, location is everything in this situation, because these clouds are going to have on-ramps. These services are going to have access points in very, very specific metro locations that bring their customers to the locations that have lowest latency to their own resources. So you want to look at your landscape and see where it's most important for you to be from a network path perspective. Where are you going to be sitting that puts you right next to your resources that you're using in your most important clouds or locations and environments? You want to be able to benefit from those access points as much as you possibly can. Now, most of the customers that we have about 2 to 3 hubs in about 3 to 4 regions. So we have 2 illustrated here, but really you're going to have probably a 3rd region and a 4th region potentially as well. And what this does is actually it keeps traffic local to the hubs and local to the region, meaning that you have far less interregional traffic, again, shortening that path. And that means that your network is overall going to be lower in cost because you're taking stress off of your global network. Those long paths can be much lower in bandwidth overall. I do have a customer, a travel company, that needs to share travel pricing information and all sorts of information between all sorts of different stakeholders. And so for them, 2 to 3 hubs in one region actually isn't enough. So what they've built is actually far more hubs in any given region. And that's because for them, every microsecond counts and they have to lower latency. And so what they did is actually they built these hubs not just to securely connect to their cloud providers, but also to the travel pricing websites, to the hotel chains, to the payment providers. All of those stakeholders have direct virtual private connections to this travel company. And what that allows them to do is it allows them to scale that connection up and down on demand as they need, even during peak travel times. But that actually only works because that travel company followed the second principle, which is to standardize everything as much as possible. Now, this is really key. You want to make sure that everything operates as much like Lego bricks that you can build up and down in different ways as possible. So you want to have landing zones in each location that are completely independent of any one clouds or environments, technology, or terminology. This is going to give you the freedom to use the best technology for you, no matter where your workloads happen to be or happen to go in the future. You also want to build up your infrastructure as much as possible using infrastructure as code, because that's going to remove a lot of human error and make it possible for you to create things again and again using the same blueprint. And that's super important. Now, you're going to bring your security edge into these hubs because that's going to make it possible for you to have a very standardized and simple security landscape where a remote user here is always hitting your hub first and then going out to any of their services that they need. Now, because these paths are short, they're still going to have great performance there and low latency, but they are getting the best security in a standardized way. And that's because things like identity and encryption and inspection tend to drift the fastest unless they're standardized at the policy layer and then deployed via automation from your hubs. So you want to make sure that's there. I had a logistics customer, for example, that followed exactly this. And what they set up is a router, an SD-WAN, and a firewall in all of their hubs around the world, and then connected privately out to their clouds and had last mile connectivity out to their on-prem locations. And they did this after they had been hacked. And the point was that they needed to make sure they understood where their security policies were and how they could manage them as simply as possible. And this was the pattern that they used to get that done. Now, once you have your hub locations chosen, again, really important to make sure that where you are is the best place for you in terms of connectivity options, then you have everything standardized. The last principle is that you want to optimize your connectivity for your use cases and workloads that are most important in your company. So you want to look at the priorities that you have and think about what makes sense for each of the environments that you're in. And because these are short paths and short connections relative to what they could be, you have a lot more to choose from in all of the options that exist within your hub. So every workload is going to have its own tolerance for things like latency and throughput, RPO, RTO, cost and security, of course. So just think about every environment and what the priorities might be there. A financial services customer of mine is a very common example of what often happens, which is they have a massive Oracle landscape, an estate here really of Oracle databases in one cloud. But in another cloud is where all of their apps live. So they need these apps to access that data. Constantly it's pulling there. And when they were doing this via public internet, latency was a huge constraint. They couldn't get the throughput they needed. The performance was really bad. And of course, data egress was a topic, right? Their bills were adding up. So what they did when they followed this pattern is they used local access points in a hub to create sub-millisecond latency between both clouds using virtual router as a service in that hub. So that routing as a service allowed them to have virtual connectivity that was resilient and that was performant for them. Now, there were still data egress charges, but because they were using private connectivity, it was much lower. And these connections could scale up and down on demand. So when they needed to scale, they could. So take a good look at where your workloads are and what kind of connectivity they might need. You should have a wealth of options inside of these hubs. For example, if your primary cloud has a lot of sensitive data and you need high bandwidth going there, you might want a dedicated physical connection running MACsec encryption to that cloud. On the other hand, if you have an environment in which you don't have such mission critical workloads running there, you can have just an internet connection going from the hub into that environment. So you might want to have shared services via VPN going out to subsidiaries directly, or maybe you have customer groups like the travel company. All of this should be possible by using that standardized architecture in the hub. And the point is that you can iterate on this. You can take one connection out and put something different in as your business grows, changes, pivots. Now you hold the levers and the control in order to make this all happen. So every organization is going to do this differently, of course. And as long as you keep the three principles in mind, to anchor those hubs in the connectivity dense neutral locations and standardize the infrastructure using infrastructure as code, for example, like Terraform templates, and then just make sure you're optimizing that connectivity, then you're going to have something that can scale and that is sustainable for the future of your business. So if you're interested in learning more, you're more than welcome to reach out to us at Equinix. And in the meantime, thank you so much for watching.